Hello, hello. You're very welcome to the very first lecture of the physics lecture series by your very own personal physics tutor, Dr. Rima McMullen. That would be me. I want to open this lecture by posing a question for you. My question for you is, what is your first memory of physics? What is that first thing in physics that you learned that you remember to this date? I'm very curious to know your answer. Please let me know your answers in the comments section. Let me guess what your answer was. My guess is that you're thinking of the story of a man who was sitting under an apple tree, and he sees an apple falling from the tree toward the ground. Now, this was certainly not the first time that he ever saw an apple falling toward the ground, but this was certainly the first time that he asked himself a question: why is this apple falling toward the earth and not flying off in some random direction? What was the name of this guy? Do you know? Let me know in the comment section who you think this guy was. Yep, you're right. He was none other than Sir Isaac Newton. And this question led to the development of the theory of gravity. Was my guess correct? Is this what you had thought of? Is this the first thing that you had ever learned? Now, why did I think that this would be the first story of physics that you ever learned? Well, that's because this is the first story of physics that I ever learned. This story was told to me by my mom when I was quite young. Maybe like 8 or 9 years old at the time. Now, I would call Sir Isaac Newton as the pioneer of physics, of mechanics to be specific. Now, Sir Isaac Newton was certainly not the first person to study physics. We have all heard of Aristotle and Galileo, who lived before Newton and studied physics. But Newton was the first person to formalize physics in terms of mathematics. In fact, he invented a whole new branch of mathematics to solve physical problems. What was that branch of mathematics? That was calculus. Now, of course, there's a controversy around that. Leibniz and Newton, they both developed calculus independently at around the same time. And to this date, it is not known who came up with calculus first. They both came up with calculus at around the same time, and we'll never know who did it first. Anyway, that doesn't matter anymore. So Newton studied mechanics. And in olden times, mechanics was the study of the celestial objects' motion, that is, the motion of the heavenly bodies. And Newton formalized it and he came up with modern mechanics. In modern mechanics, we study the interaction of the objects with each other, what kind of forces they exert on each other, and what is the motion of those objects as a result of the forces that they exert on each other. Okay. Now, this course, it is devoted to mechanics. Let's look at a simple yet instructive example to see what kind of problems you might come across in mechanics. Let's say you have a box of mass m sitting on the ground. You apply a certain force F, and as a result of this force, the box slides across the floor a distance d. So the box ends up over here. So you applied some force and the box now moves over here. And it moves the distance d. And it takes time t to move. So when you first apply the force on it, it starts with a velocity v naught. That is the initial velocity of the box. And it comes to rest over here at its final position. And it travels a distance d. Now this relationship between how much force you're applying and as a result of that force, the box starts out with what kind of velocity v naught. How much distance d does it travel before it finally comes to rest? And what's the time taken to travel that distance d? The relationships between these things, it's studied in mechanics. Let's look at one more example. Let's say you're driving from New York to Los Angeles. What's the distance between New York and Los Angeles? It's about 3,000 miles, give or take. Now, let's say you're driving from New York to Los Angeles at an average speed of 100 miles per hour. Okay. How long would it take for you to travel this distance? 30 hours? Are you with me so far? So, what we are saying is that the distance, I want to use a different color. Why? Why not? Distance between New York and Los Angeles is about 3,000 miles. You're driving with an average speed of 100 miles per hour. And at this speed, it takes you 30 hours to travel 3,000 miles. Now, these things that I'm writing, speed, distance, time, what are these things? These things are called as physical quantities. What is a physical quantity? Let me make it singular. What's a physical quantity is something that can be measured or calculated. Can be, you can either measure it or want to make sure it fits on the screen. That's why I keep looking in that direction. That's where my monitor is. That shows me if this thing is fitting on the screen or not. So we define physical quantity as anything that you can measure or you can calculate. Now let's look at what can we measure. Can we measure time between two events? Sure we can. Can you measure the length of this pen? That's distance or length. Can you measure mass of an object? Yes, you can. Can you measure force applied on an object? Yes, you can. What else can you do? Let's say you have this cube of side length A. Can you calculate its mass? Sure you can. It's going to be A cubed. Can you measure its mass? Let's say you measure its mass and you divide it by the volume of the box. What does this give you? This gives you the density of the box, correct? And let's say you apply some force F on this box, on the surface. Then this force F divided by the surface area. What does this give you? This gives you pressure. So all these things, pressure, density, volume, mass, force, time, length, moment of inertia, momentum, angular speed, angular velocity, torque, all these different things and many more that you're going to see in mechanics, these are all called as what? Physical quantities. Once again, a physical quantity is something that can be measured or it can be calculated. And we have seen quite a few examples of these. So there are two ways of categorization of physical quantities. Let's look at the simpler of the two first. Every physical quantity can be categorized as either a scalar physical quantity or a vector. Now, a scalar physical quantity has magnitude only, while a vector physical quantity, it will have magnitude as well as direction. What does magnitude mean? What do you think magnitude of a physical quantity is? Let's say you're buying a bag of rice, and the options you see are you can buy 1 kilogram bag, 2 kilograms bag, 5 kilograms, 10 kilograms, or maybe 20 kilograms. Okay? Now, this number 1, 2, 5, 10, 20. What is this telling you? It's telling you how much rice you're getting. You know that in 2 kilograms per bag, you're getting twice as much rice as you're getting in 1 kilogram bag. So this number, this represents the magnitude. And what does magnitude tell you? How much? Whatever it is that you are talking about, whatever that physical quantity is, how much of that is there? That is represented by the magnitude of the physical quantity. Now, direction, in the case of vectors, you all know what direction means. So if a physical quantity has only magnitude, it is scalar. If it has magnitude as well as direction, then it is a vector quantity. Now, which ones are scalars? Scalars include mass, temperature, time, speed, distance, and so many more. As I introduce each new physical quantity, I will tell you at that time if it's a vector quantity or if it's a scalar quantity. Just to give you a few examples of vectors. Okay? Vectors. You have force, pressure, momentum, torque, velocity, acceleration. I mean, I can keep on going for a very long time, but like I said, as I introduce each new physical quantity to you, at that time I'll tell you if it's a scalar quantity, that is, it has only magnitude, or if it's a vector quantity, that is, it has magnitude and direction both. So, this is one way of categorization of physical quantities. Each physical quantity will either be a scalar or be a vector quantity. The other way of categorization of physical quantities is each physical quantity will either be a base, okay, also called as fundamental. P dot Q dot is physical quantity, or it will be a derived physical quantity. Now, a base quantity or a fundamental quantity, as the name suggests, it's fundamental. That means you cannot break it down any further. You cannot describe this. You cannot put this in terms of any other physical quantity. Okay? In mechanics, there are three base physical quantities, and they are mass, length, and time. In physics, there are four more fundamental quantities, and in this lecture, I will provide you a list of all of them. Okay? But for now, I'm looking only at the fundamental physical quantities in mechanics. In mechanics, there are only three fundamental physical quantities. These physical quantities, they cannot be written in terms of anything else. While derived physical quantities, like the name is telling you, they are derived. They are derived in terms of what? In terms of base physical quantities, right? So, for example, let me bring this back. If I say speed, what's the formula for speed? Distance divided by time. Distance is length. That's what you're measuring. When you're measuring distance, you're measuring length. And time is over here. So time and length, these are both base quantities. You take the ratio of these two base quantities to calculate speed. So speed is a derived quantity. And if you were to figure out, okay, velocity, it's very similar to speed. That's going to be displacement, which is again length over time. Acceleration, that is change in velocity over time. So velocity is in terms of displacement over time. And displacement is length. Time is, well, it's time. So displacement and time, they are both base physical quantities. So velocity is derived in terms of two base quantities, which are length and time. Next, when we move on to acceleration, acceleration is derived in terms of velocity and time. But velocity itself was derived in terms of displacement and time, which were base quantities. So acceleration is also broken down into the terms of displacement and time. Now, if I move on to force, force is mass times acceleration. We just said that acceleration can be broken down into velocities and time, these physical quantities. But velocity can be broken down into displacement and time, which are base units. So acceleration is written down in terms of base physical quantities of displacement and time. And mass is already a base physical quantity. So there, force can also be broken down into base physical quantities. All these: speed, velocity, acceleration, force, pressure, momentum, moment of inertia, angular momentum, angular speed, all these things, they can be written down in terms of mass, length, time. Three base fundamental quantities of mechanics. But like I said, this is not all. This is not all. We have more fundamental quantities. In physics, now we are getting out of just mechanics. Physics has many more branches. So at your level, you're likely going to see mechanics at first in 11th grade. Then you will see properties of matter, right? Waves and equations, waves and oscillations, I mean. And next year, you will see electricity and magnetism, optics, electronics, and a little bit of astrophysics, right? So physics has several different branches, okay? In all of those branches combined, we have total of 7 base physical quantities. So there are 7 base, or you can call them as fundamental physical quantities. We have already looked at 3 of them in mechanics, which are mass, length, and time. What are the other ones? We have electric current, amount of substance, number 6, temperature, and 7 is luminous intensity. So these are the 7 fundamental physical quantities of physics. Now, mass. When we're talking about mass, mass is a measure of inertia. Okay, so that's the definition in physics. In chemistry, you will see the definition of mass as it's the amount of substance something has. That is its mass. Okay. In physics, we say that it's a measure of its momentum or a measure of its inertia. Now, how do you know how much mass something has? Okay. So you will say that it is maybe 2 grams, maybe it is 70 grams, maybe it is 500 kilograms. So this thing that it follows after the number, right? So if I say that 70 kilograms, this 70 is the magnitude of mass and kilogram is the unit. So let's next look at what is the unit of measurement of a physical quantity. P dot Q dot is physical quantity. It is the reference with respect to which you will measure how much of physical quantity is there. Okay? It is reference WRT, with respect to which you measure how much of physical quantity there is. What does that mean? Let's say I have this pen over here, right? You see this? I want to measure the length of this pen. What would I do? To measure the length of this pen, I would likely use a ruler. I can measure this in inches or I can measure this in centimeters, right? If I were to measure the diameter of this pen, maybe I can use a ruler and get an approximate value of the diameter. But if I want to be more accurate, then I would use something called as vernier caliper. Okay? If I were to measure the tip of this pen, tip is the part that I'm using to write with, then I will use something called as micrometer. Okay? Now to measure, to get the length, length will probably be either in inches or in centimeters, right? The diameter might also be either in centimeters or millimeters, right? And the tip will be either in millimeters or micrometers. So all these different things that I've written here, inches, centimeters, millimeters, and other millimeters. Let's cross it out. Micrometers, it could be nanometers, angstroms, femtometers, and there's so many more ways of writing down units. I could write down length in miles, right? I could have length in yards. I could have length in feet. I could have length or distance in light year. Which of these units would I pick? That depends on what I'm measuring. If I'm measuring the length of this pen, I'll use a ruler. I will measure the length either in inches or in centimeters. If I'm measuring distance between two houses on a street, I will probably use units of either meters or yards. If I were measuring the length of my street, I will probably measure it in meters or maybe in kilometers, depending on how long the street is. If I'm measuring the distance between two cities, I will probably measure it in either kilometers or miles. If I'm measuring distance between two stars, then I would measure that in light years. So the unit that you're using to measure something, that depends on the quantity. Like, what's the size of the physical quantity? How much of, what's the magnitude of that? And of course, magnitude will depend on the units. But I think you get what I'm trying to convey to you, right? I think you get it. Units of measurements. Now, there's more than one system of unit of measurement. One system of unit of measurement is CGS. C, centimeters, right? G, gram. S, second. So these are the units of the base physical quantities: mass, length, time. CGS, centimeter, grams, seconds. Then we have another system called as FPS. F, foot. P, pound. S, seconds. Now, which of these three is the unit for distance? Foot, right? How many inches are in a foot? 12 inches. 1 yard. How many feet are in a yard? 3 feet. Okay. These are important things that I think everybody should know. Pound. Now, pound, technically speaking, is not a unit of mass. It is actually a unit of weight. Okay. So weight is not same as mass. But for now, it is sufficient to know that pound is actually a unit for weight. It's not mass, but weight and mass are actually related to each other. Weight is mass times acceleration due to gravity. Okay. And second is, well, that's just seconds, right? Everybody knows that's the unit of time. CGS, FPS, last, MKS. So now you tell me, this M, what is this going to stand for? Meter. K, kilogram, right? S, I bet you can never guess what S stands for, or did you? Seconds. So now, another very important thing, physics, chemistry. These are case-sensitive subjects. Meter, you will never use uppercase M, always lowercase m. Kilograms, lowercase k, lowercase g. Now, granted, I have seen uppercase k, lowercase g written for kilograms, but it's lowercase k, lowercase g. And seconds is lowercase s. Now, MKS, these days it is called as the SI system of units, System International. And this is the scientific system also. Now, SI system is also a metric system. What does metric system means? It means that the different units of a physical quantity are related to each other by powers of tens. What does that mean? Do you know? 1 kilogram, 10 to the power 3 grams. 1 nanometer, 10 to the power negative 9 meters. 1 femtoseconds, 10 to the power minus 15 seconds. 20 megagrams. 200 megagrams. 200 times 10 to the 6 grams. And this is lowercase g, by the way. So you can see that to go from one unit to the other, all I'm doing is multiplying or dividing by 10, right? Some powers of 10. Going from kilogram to grams, 10 to the power 3. Nanometers to meters. Now you're dividing actually by 10 to the power 9. When you say that you're dividing by 10 to the power 9, that's same as multiplying by 10 to the power negative 9. So I hope you see what I'm trying to show you here. These are very, very basic fundamental things that you have got to know before you start doing physics. Now over here, I had introduced 7 fundamental physical quantities in physics. And now we know what SI system of units is. Let's look at what are the SI units for these physical quantities. Mass, we just said, is kilograms. Length, meters. Time, seconds. I'm not going to spell it out for these 3 because I believe you know how to spell them. Electric current. Symbol for it is A, uppercase A, and it is called as ampere. Amount of substance. The symbol is lowercase m, lowercase o, lowercase l. It is mole. Temperature, uppercase K, for Kelvin. Luminous intensity, candela. 3D, lowercase c, lowercase d, for candela. There you go. These are the SI units for the 7 base fundamental quantities. So in this lecture, we have looked at, just to give you a quick recap. In this lecture, you learned what a physical quantity is. That is anything that can be measured or it can be calculated. Okay. Then we saw that there are 2 systems of categorization of physical quantities. Every physical quantity is either a scalar physical quantity or it's a vector physical quantity. And also every physical quantity will either be derived physical quantity or it will be a fundamental physical quantity. Then we looked at the different systems of units of these physical quantities. And this is actually the foundation of everything else that you will learn in physics. Now, very quickly, tell me, let's very quickly look at these four physical quantities and see if they are derived, base quantities, scalar, or vector. Speed. Is speed derived or is it base? It's derived. It is not base. Is it scalar or is it vector? Speed is a scalar quantity. It's not vector. Electric current. Is it derived or is it base? We just said electric current is a base physical quantity. Is it scalar or vector? Well, it is a vector quantity. Temperature. Is it derived? Nope. It's a base physical quantity. Is it a scalar or is it a vector? It's a scalar physical quantity. Force. It's a derived physical quantity and it is vector. So every physical quantity will either be base or derived. So see, it's one or the other. And same thing here, it's either a scalar or a vector physical quantity. All right. So in the next lecture, lecture number 2, we're going to go over the dimensions of different physical quantities, how to get the dimensions of them, how to get the dimensional formula of them. What is the significance of dimensional analysis? And what kind of rules exist around them? Okay. So don't go away. Come back. So see you very soon in the next lecture.